last time we have started the another aspects of photochemical reaction, that is photocatalysis. We have discussed about uh, the principle involved in photocatalysis, and we have also discussed. We have also been involved in the work related to this, and what we have done has already been shown in the previous slide. So we have studied a large number of for pesticides, drug, and dyes, the degradation of those compounds in the presence of. The main the topic is the photocatalysis, and this is a heterogeneous. This involves heterogeneous photoinduced electron transfer reaction. This, as I have mentioned before, this work has started with a great aim from environmental application for detoxification of wastewater. I mean, the degradation of organic and inorganic components present in water, and the reaction takes place in aqueous suspension. So this is an advanced oxidation process, and with a search to look for an most economical and viable method for detoxification of water. I mean, the degradation of organic component present in water. So this has started with this aim, and a lot of work has been done previously and is still going on. And then today also we will discuss some of the work related to this. From application point of view, the most important aspect is to standardize the reaction condition in the laboratory scale. I mean, which catalyst is most active, and at what pH the reaction is taking place means highest efficiency, and what should be the pollutant concentration, what should be the catalyst concentration. And it has also been found that the electron acceptors or electron donor or electron acceptors, or we call it as a scavengers, also plays an important role in taking important role in the degradation efficiency of the compound. So as far as the type of catalyst is concerned, we are at present several other single semiconducting material like titanium dioxide, zinc oxide, tin oxide, bismuth oxide, and so on and so forth has been investigated, of which the titanium dioxide has been found to be the most active catalyst. And then this is present in two different forms, such as rutile and enantase. So the different catalysts have been available commercially, and then we have tested and some of the commercially available. So we are just concentrating on the photocatalysts such as titanium dioxide, which is available commercially in different forms, such as is the most the widely used is the Degussa P25, is a form of titanium dioxide. Another form of titanium dioxide is Hombicat UV100. This is has been produced in Germany, and this is is present all over the world. Is available in US, India as well. It has a company in Bombay, and then the other is a titanium dioxide PC5. It is Millennium Inorganic Chemical produces the titanium dioxide. The India, this is from Travancore Titanium Products from India, Kerala. Kerala is available this one commercially. So 4 different types of titanium dioxides are available, and we have tested all these 4 titanium dioxide samples for degradation of different compounds such as pesticide and drugs, just to see which form of titanium dioxide is most active. As you can see that these titanium dioxide samples have a different composition. First one is the Degussa P25 consists of 80% enantase, and it's a mixture of 80% enantase and 25% rutile. and it has a BT surface area of 50 meters square per gram, and the particle size is 20 nanometer. On the other hand, Hombicat UV100 from the sample from German company, it has a 100% NATs, whereas it has a BT surface is very high, something around more than 250 meters square per gram, and size is just 5 nanometers. So we'll see these samples differ in the surface area as well as particle size, as well as some are mixture of NATs and rutile, and some are pure NATs. The titanium dioxide produced from millennium inorganic chemicals also is 100%. The form which we have tested is the PC500, is 100% NAT. It has a BT surface of 287 meters square per gram, and particle size is 5 to 10 nanometer. On the other hand, Travancore titanium products TTP sample obtained from Kerala, India, is also 100% NAT, and BT surface is very less, is around 9.82 meters square per gram. So these we can say that we have 4 different samples of titanium dioxide having different characteristic feature, and then we would like to see how these titanium dioxide differ in reactivity for the degradation of different organic compounds. Our results are shown over here. You can see that these 4 different titanium dioxide, PC500, UV100, P25, UV100, PC500, and TTP products, and all these 4 have a different characteristic features, have been tested for degradation of this particular the pesticide, and then we can say that this is the degradation rate for this using these pesticide. And we can see that each titanium dioxide has 2 different bar. One is for the this is black, one is for TOC, means the mineralization rate. So this is the mineralization rate, this is the degradation rate. This is degradation rate was followed by using UV spectrophotometer, whereas mineralization rate was followed by measuring the TOC decrease in total organic carbon content from all the way from 0 time irradiation to different time intervals. And then this is again is the same one for 4 different samples of titanium dioxide. You can see that the the activity of sample obtained from Degussa P25, that is PC500, is most active as far as the degradation as well as mineralization is concerned, as compared to all the 3 different samples available. Although you can see that the UV100 is 100% NATs, which is photoactive. I just want to mention here that out of these NATs and rutile, NATs form is photoactive, whereas rutile is not photoactive, and that's why rutile form of titanium dioxide is used in paints, so that is not get faded in the color of the paint. So you can see that although the UV100 is 100% NATs, which is photoactive, is less efficient for degradation as well as mineralization of this particular compound. So so it is not only the NATs form, but different factors are also involved. This has a 100% NAT as well as a lot of surface area. Surface area is also very high in these 2 cases, as well as compared to P25. But although the activity of P25 is better as compared to the other higher surface area as well as 100% NAT sample. So the results could conclude that the P25, why the P25 is most active as compared to UV100, which is 100% LH and large surface area. The reason could be rationalized in terms of the fact that PC500 is composed of a mixture of rutile and NATs. The rutile has the smaller band gap and which catches photons most efficiently, generating electron hole pair. So this could be a reason for better activity of P25 in the case of P25, which is a mixture of anatase and rutile. The electron transfer from rutile conduction band and it traps the is trapped from the. So, for example, this is the band gap of rutile is band gap of anatase. So, this excites most efficiently because of lesser band gap, smaller band gap goes to an electron band and then it transfers to the and then this back electron transfer is prohibited. The rebound and that's why because of this transfer to the anatase form, the back electron transfer is removed by the surface particle reacts with this. So, so not only we have also and the results for these three different samples of titanium dioxide has been tested for this particular dye, and we have tested the degradation of this dye with the UV100 piece. Degussa P25 as well as PC500, and you can see that in this particular case UV100 is found to be much better for both degradation as well as mineralization. This is TOC and this is UV. UV determines the degradation, the decrease in color, and other one is determines the total organic carbon. Conversion of organic carbon to inorganic carbon means mineralization. So you can see that it is not only not only the is always not effective. You can see P25 better in this particular case, whereas UV100 is better for this particular compound. So we can conclude that the chromophore present in the molecule is also important as far as the type of titanium dioxide sample is concerned, which differ in surface area as well as the in surface area, particle size, as well as the anatase or rutile mixture or a pure anatase. So in this particular case, UV100, which has a high surface area, 100% anatase, is much more efficient as compared to the P25, which is a mixture of anatase and rutile, and which shows better efficiency for degradation of this particular dye. So it is the important. So what could be the reason? The reason for better activity of UV100 could be rationalized in terms of fast interfacial. So since fast interfacial electron transfer is taking place in UV100, this could be the higher efficiency for better, and also, as I have mentioned, it also depends upon the type of chromophore present in the molecule. Because UV100 expect higher efficiency, would expect higher because of the higher surface area, and which lead to better desorption of the polyethylene is relatively faster, and recombination of electron hole period is prevented. Electron hole period with suitable electron acceptor or by reaction of hole and scribe. So these are the few reasons which could be rationalized due to the fact that UV100 is better in this particular case. This is due to fast interfacial electron transfer rate, and also depends upon what is the type of 4%, and there is a higher efficiency because of the better higher surface area, because you can see here UV100 has a 250 meter square, and this is just a 50 meter square. So higher surface area lead to better absorption, desorption, and fast recombination rate, and hole is prevented. And because of this, the recombination rate is prevented, and it got enough time for the reaction of electron plus reaction of oxygen to generate superoxide radical anion, and hole to transfer to the water transfer to hole to generate to hydroxyl radical. And initially we mentioned that these two species are main important reactive species, which is all in the degradation of these molecules, and these are relatively having better separation and better time. In these reactions are surface reaction taking place on the surface of the reaction, because it is a heterogeneous reaction. The catalyst is neither soluble in water nor in organic solvent, and then and that's why the pH is an important parameter in these surface reaction, because in the case of titanium dioxide, in the presence of acidic medium which will generate H plus, can the surface of titanium dioxide will be like this, TiOH2 plus, so it is a positively charged. On the other hand, titanium dioxide in the alkaline medium, it will be the TiO2 becoming TiO2 becoming negatively charged. So Ti is here, and then OH2 plus. So you can see that the surface of the titanium dioxide can be positively charged under acidic medium, as well as negatively charged surface on the medium. And not only that, the pollutant, say for example, this is a dye. It has a oxygen, and it can also be protonated in the presence of acidic medium and deprotonated, and this also has a NH protons which can be protonated, deprotonated under acidic conditions. So both pollutant as well as the surface of the catalyst can be in different form depending upon the pH of the solution. So pH plays an important role in the surface reaction, and that's why the pH dependent reaction is important to measure which pH is at what pH the degradation is maximum, and what is the optimal pH for the higher efficiency for degradation or mineralization of different pollutant used in these cases. And that's why you can see that this is the degradation rate at different pH values, and this is the pollutant. This is a pesticide which we have studied, and we can see that this is the rate of mineralization, TOC, and this is for degradation monitored by UV. And then we can see that both the degradation as well as mineralization for this particular is higher under acidic pH, around 3. And when we go the reaction to the lower pH value, the degradation decreases, and that's why we can say that the pH is really playing a very important role in the degradation of this particular compound. Its highest efficiency was observed and under acidic pH, which slowly decreases going from neutral to basic alkaline pH values, and hence we can say that the pH is highly dependent for get better degradation efficiency. Here is another pollutant. We can see is an azo dye, and which and the degradation of this particular dye has been tested. There's a degradation rate versus a different pH value, and here just a reverse of this is for TOC, and this is for UV degradation, and this is TOC mineralization. You can see that the lowest degradation efficiency was observed in the lower pH values, just a reversal of the earlier result, and then the rate of mineralization as well as rate of degradation both increases when we increase the pH, and highest efficiency was observed when the pH of the reaction mixture was at around 10. So you can say that the pH of the pollutant, because at different pH pollutant can be protonated and deprotonated, and also at different pH, the surface of the titanium dioxide can be protonated, deprotonated, and we know that in surface reaction, the adsorption is the prerequisite for degradation. Better adsorption leads to better degradation. So it can be assumed that in these cases the better adsorption is taking place, and that's why we get a highest efficiency in acidic pH, whereas on the other end, in this particular case, the better adsorption takes place at. Not only that, in high, the other reason could be for better results of better degradation efficiency in alkaline pH could be there is a possibility of generation of hydroxyl ion in alkaline pH, and which may lead to the degradation of the pollutant more efficiently. Another important, I would like to mention here that in the the pH of the reaction was maintained throughout through the addition of a buffer continuously. If it is decreasing, if it is I mean, say for example, we have done the pH at 3, so we see that the pH of the reaction mixture remains 3 throughout the reaction. If we do the reaction at pH 10, we make sure that pH of the reaction mixture throughout the irradiation, whatever be the irradiation time, whether it is 1 hour or 2 hour, remains same through the addition of a buffer of either HCl or an NaOH, because we have an arrangement to add simultaneously the H plus ion in the nitric acid or aqueous solution of NaOH when the pH decreases or increases from the fixed reaction pH. Now we can see that we would like to see what could be the optimal catalyst concentration for better efficiency, and then this is the degradation of this particular pesticide derivative. Again, in both the cases we have followed mineralization as well as TOC, and we can say this is the catalyst concentration and this is the degradation rate. This is the increase in the catalyst concentration from 0.5 gram per liter to 1 gram to all the way going to 3 gram per liter. You can see that when the catalyst concentration increases from 0.5 gram per liter to 2 gram per liter, rate of the reaction is increases all the way from 0.5 to 1 to 2, and then the further increase leads to it doesn't make much difference, and that's why it is the saturation catalyst, and any further addition does not make any difference, and that is the leveling. We can say that the same rate observed even we go from 2.5 to 3 gram per liter, and then so for this particular catalyst, for this particular pesticide, 2 gram per liter is the optimal condition for best efficiency degradation or best degradation rate for this particular compound. The substrate concentration dependence is also important, because in the case of colored compounds, when the color is becoming very strong or very dark, then the catalyst hardly get any light, and that's why the substrate concentration is also important. We can see this is the substrate, this is the pesticide derivative degradation rate, and this is we have varied the substrate concentration from 0.2 millimolar all the way going to the 0.6 millimolar, so 2.5 millimolar. You can see when we increase the substrate concentration slowly, with the increase the substrate concentration, there is an increase in the degradation as well as mineralization, because more and more substrates are there, and it will be degraded very fast. But again, after this, there is a leveling effect, and then after increasing the substrate concentration from 5.5 gram to 0.75 gram per millimolar does not make many difference. So we can say that this substrate concentration is an optimal concentration for highest degradation rate for this particular compound. So it is not only it is again vary from substrate to substrate. This is another substrate, and we can see we have also seen the substrate dependence reaction, and we can see that lower, and then again it increases to some extent with the increase in substrate concentration, and then decreases, and then there is a decrease in so this is a dye, and when the substrate, as I have mentioned, when the substrate is very high, the solution of the irradiating solution becomes very dark, and the light is hardly falling on the catalyst for enable it to generate electron hole pair and then to generate active species, and that's why so it is. We can see that it is not only the highest concentration, but there is so the important aspects of determining the optimal condition is very important. And then we have seen that here this is the substrate concentration, say we around the 0.35 millimolar concentration is if optimal, giving the highest degradation rate in this particular case, and there is a further decrease is observed in this case. So, and here is not a decrease, but there is a leveling effect of the physical. This is a colorless compound, and then this is a colored compound, and then when we increase the concentration of the dye, solution becomes very dark, very intense, or very strong, and then hardly gets excited catalyst, and then so another aspect is the additive concentration, which is also plays an important, as we can see that the most drawback with this is a fast back electron transfer and the fast back electron transfer. So in order to how to increase how to decrease the back electron transfer can be done by involving the scavenger which can abstract this, and then that we have done with the addition of a electron acceptor, which will and these are the results which will continue on the next term. Thank you very much.